Welcome to EPG Pathshala. Today we will be learning a few new things: product space, product measure and Fubini's theorem. Fubini's theorem plays a very important and crucial role in many fields. For example, multiple integral, computation or computing expectation. We have several examples. So far, what we have learned, the concept of measure on a single dimension, we will try to extend that concept for more than one dimension. So we will be considering measure space, product measure, product space and Fubini's theorem. And this tutorial or this lecture will be concluded with some application of this Fubini's theorem. The proof of the Fubini's theorem, though it will be stated a bit sketchy because we don't have that much time, but it can be found in any standard book. But the main thrust will be on the application as well as the concepts of this Fubini's theorem, which we use widely in statistics and mathematics too. To start with the deliberation, we will define a few concepts before going to the most important Fubini's theorem, which is the primary objective of this lecture. In this lecture, we will first define what do we mean by product space, then product measure, and then we will describe Fubini's theorem and how this Fubini's theorem can be applied into different problems. I will discuss a few. So let us begin with few of the definitions that are necessary to define product measure. We know that in real line we have the Borel sets, which are the open sets. So if I consider the k-dimensional Borel sets Bk in k-dimensional real line Rk, then these Bk in Rk are generated by open sets. We can generate these open sets by rectangles. For example, R is J1 into J2 into Jk, which are products of intervals Ji. Each of these Ji's, they are intervals. Now we consider the C as the collection of all rectangles that can be constructed using these products. And it can be seen that this Bk, this is a k-dimensional space, what we are talking about, is nothing but the sigma space or sigma field generated by C. This is the collection of all rectangles. So this means that the Borel sets are the smallest sigma field containing all rectangles in Rk, k-dimensional real line. Now it is necessary to distinguish between measurable rectangles and rectangles. So if we consider only rectangles, they are the products of intervals in real line, and among these rectangles we have measurable rectangles. These are the products of arbitrary Borel sets in R1, that is the real line. So it is very important to differentiate between measurable rectangles and rectangles. So now we have the first definition. The measurable rectangles D in R are the collection of products of Borel sets. So by D we mean is a set of B1 into B2 into Bk, where each of these Bi's are Borel sets in real line. So we are taking the product of these Borel sets and we are getting a collection as D, and we call this D as measurable rectangles. And we know that Borel sets are the smallest sigma field generated by C. But what about the sigma field generated by D? Well, we have one lemma that says that the Borel sets are the same as sigma D. And the proof is something like that, to show that sigma D is contained in Borel sets Bk, that is the k-dimensional Borel space. So if these Ji's are open intervals, then J1, J2, Jk, this product will belong to Bk, k-dimensional Borel space. Furthermore, the collection where J1 is replaced by A, and if I take all the collection of such A, that A into J2 into J3 into Jk belongs to Bk is easily seen to be a field which contains interval, and so it must be in B. Thus, for any B1 which belongs to B, it follows that B1 into J2 into Jk, they are also in Bk if Ji are all open intervals. So, if we use this argument similarly, we can see that if we have considered B2 which belongs to B and Ji are all open intervals, then B1 into B2 into J3 into J4 into Jk, that will also belongs to Bk. Continuing this way, we conclude that B1, B2, Bk belongs to Bk, is the k-dimensional space. So, for Borel Bi, so it shows that sigma d, this is a sigma field generated by d, is a subset of Bk, and this shows that this sigma field is nothing but equals to Bk. Now recall that Lebesgue measure M, we know that Lebesgue measure M on k-dimensional real line Rk is defined by extending its from the rectangles C uniquely. So if we extend the concept of Lebesgue measure in k-dimensional real line and Lebesgue measure we extend it to the rectangles, then we can do it uniquely. It is also easily shown that it can be shown that M can also be extended from the measurable rectangles D uniquely, because if I consider all Bi belongs to B, it is easy to note or easy to show that M, the measure of this product B1, B2, Bk, is MB1 into MB2 into MB3 into MBk. Note that products of measures mu I on R, this is a real line, can be defined analogously to Lebesgue measure on products of copies of real line. So specifically, if we take mu I is a Borel measure in R, then we can define the product measure mu as mu1 into mu2 into mu3 into mu k on Rk, this is the k-dimensional real line, as follows. We can recall that this k-dimensional real line Rk is the collection of x1, x2, xk, where each of the xi's are real numbers. Now we consider that Bi belongs to B, this is the Borel set in the real line, and we have B1, B2, B3, Bk. So you can similarly define mu of B1 into B2 into Bk as mu1 B1 into mu2 B2 into mu k Bk, and extend this to k-dimensional B, that is Bk. So now we will have a theorem that there exists a measure mu on Rk, this is the k-dimensional real line, defined by mu B1 into B2 into Bk as mu1 B1, mu2 B2 and mu k Bk. Of course, this definition generalizes to any product of measure spaces. So consider two of them, x script x mu into y script y and gamma. So we have two measures, mu and gamma. Then the omega is product of x and y. This is the collection of all x and y, where x belongs to script x and y belongs to script y. On this sigma, we can define a sigma field. On this omega, we can define a sigma field f script f as sigma field generated by A cross B, where A belongs to script x and B belongs to script y. And we define a measure mu or pi, which is mu cross gamma, and we define pi as pi of A cross B equals to mu A cross gamma B. So this is the measure we defined on this sigma field. Now we have one theorem that if E belongs to x cross y, so if E is a set which belongs to this product space, then for each x, for fixed x, y, collection of y such that xy belongs to E, this whole set belongs to y, and similarly for each y, if I construct such a set that its collection of x such that xy belongs to E, that will belongs to script x. Secondly, if fxy measurable, this is a measurable function with respect to x cross y, then for each fixed x, fx dot is measurable with respect to y, and for each fixed y, f dot y is measurable with respect to x. So this is the theorem we have, and I am giving a sketch of this proof. So given fixed x, the map txy, which is x and y, collection of x, y, this maps y to x cross y. And it is easy to note that the inverse image T inverse E is measurable if E is A cross B and it is a measurable rectangle. It can be proved that T is measurable since rectangles E generate all measurable sets. So that proves that, well, T is measurable and it is a measurable rectangle. So thus for any E we have Tx inverse E, which is set of y such that xy belongs to E is measurable, and if we use this, then the final claim follows easily. So this is the sketch of the proof of the theorem that we have mentioned just now. Now we consider a set E which belongs to the product space x cross y. We define Ex as Tx inverse E, and we define the function mx as gamma Ex. This is gamma function of y such that xy belongs to E, and it is easy to note or show that mx is measurable. Now we define two integrations, pi prime E and pi double prime E. Pi prime E is integration over x, all possible values of x, gamma Ex d mu x. So here it is measurable with respect to mu, and pi double prime E is integration over y, mu Ey d gamma y. So it is measurable with respect to gamma, where this set Ey is collection of x such that xy belongs to E. Now it is not very difficult to show that pi prime and pi double prime are measures. Also it is easy to show that if E is A cross B, this is a measurable rectangle. For this case, pi E will be equals to mu of A into gamma B is same as pi prime E and is same as pi double prime E. So this will hold if this E, which is A cross B, is a measurable rectangle. Once we defined everything, now we can define Fubini's theorem, which is very important. So the measure pi, which is product of mu and gamma, we define this pi as pi of A cross B is mu A gamma B, and this measure is sigma finite and coincides with pi prime and pi double prime. It is its own unique extension when restricted to measurable rectangles E equals to A cross B. For example, if we consider Lebesgue measure on R square. So Lebesgue measure on R square is mu equals to mu1 and mu2, where mu i's are Lebesgue measures. So now we will define what do we mean by Fubini's theorem, the statement. It says that if xy, fxy is measurable with respect to mu1 and mu2 and integration over mod of f d mu1 into mu2 is finite, then integration over y and the inner part is integration over x fx d mu y mu1 x into d mu2 y is same as integrating over x cross y, and fxy d mu1 cross mu2 is same as integrating over, first integrating over y, then integrating over x. This is effectively a fundamental theorem of calculus, an evaluation theorem for multiple integrals, and this theorem has been used widely in mathematics, in statistics, in probability. So everywhere this theorem is so important. So now we will try to give a sketch of the proof of this theorem. So this is the simplified version of the Fubini's theorem, and this is the version that we use for multiple integration. First of all, we will try to prove this theorem for any indicator function. Why? Because we know that if we can prove this theorem for any indicator function, then we can prove it for simple function, because simple function can be expressed in terms of indicator function. And if the theorem holds for a simple function, then we can extend this further to non-negative function, because we know that any non-negative function can be expressed as a limit of a sequence of non-negative, non-decreasing simple functions. Then finally we can extend the whole concept to any function. So we will start with the basic thing, that is the theorem for indicator function. So we take fxy as iexy, where this is the I is the indicator function, E belongs to x cross y. Then this can be extended to any simple function as I have mentioned. We can write C, the whole space, as sum over I from 1 to n ai cross bi. Then icxy is indicator function ai cross bi xy. Now this will give value 1 or 0 if x and y they belongs to ai cross bi or not. So it can further be written as sum over I of ai x, I of bi y, from which it follows that icx dot, where y is fixed, belongs to sigma field of y, script y, for each x belonging to script x. And if this is something like that, then we know that integration over y icxy d mu 2 will be sum over iai x mu 2 bi. Now it follows that given fixed x, integration over y icxy d mu 2 belongs to sigma x, and that integration over x, integration over y icxy d mu 2, which we already got, d mu 1 is equals to sum over I from 1 to n mu 1 ai mu 2 bi. So we can write this double integration in this form. Similarly, if we exchange the position of x and y, then we have integration over y, integration over x, icxy d mu 1 d mu 2 is equals to sum over I from 1 to n mu 1 ai mu 2 bi. This shows that we may write the product measure mu 1 into mu 2 c as sum over I from 1 to n mu 1 ai mu 2 bi. So combining all these three with this definition, we can have integration over x, integration over y, icxy d mu 2 d mu 1 is equals to mu 1 into mu 2 c, and this is equals to integration over y, integration over x, icxy d mu 1 and d mu 2. From either of these representations, it is easily seen that mu 1 and cross mu 2 is a finitely additive measure with the desired properties. So the basic notion or basic information that we want to give from this Fubini's theorem is that whether we can interchange the order of the integration. So if they are measurable and if they are finite, then we can do this using Fubini's theorem. We'll give one simple example that we often use whenever we are computing expectation. We do this sort of sums all the time we perform in statistics. So let's apply Fubini's theorem to prove a generalization of a familiar relationship from a beginning probability course. Let x be the non-negative integer valued random variable. Then we know expected value of x is xpx. So value into corresponding probability. Now this expected value of x can be written as I from 1 to infinity. So I am summing over I, probability x greater than equals to I. So how to prove this? We will start with the basic notation or basic definition of expected value of x. So expected value of x is sum over I from 1 to infinity, I pi. Pi is the probability, x will take the value I. So this I can be replaced as k from 1 to I, because if we add this I number of times 1, then I will get I. So I can write the whole sum as I from 1 to infinity, k from 1 to I pi. Now I am interchanging the range of I and k. So now I am writing k from 1 to infinity and I will start from k to infinity pi. These two sums are giving equal equal number if they are convergent. So finally I am left with sum over k from 1 to infinity probability x greater than equals to k. We'll show that if x is a non-negative random variable, then expected value of x is integration 0 to infinity probability x greater than equals to x dx. To prove this, we define a set A which is collection of omega and x such that x lies between 0 and x omega. So intuitively, if we assume this omega, capital Omega as the real line, then A would be the region under the curve x omega. So we argue that expected value of x will be integration over omega x omega dp is same as integrating omega and integrating over 0 to infinity. This is the range of the x, and I am taking an indicator function 1a omega x dx dp. Now let's postpone all the technical issues for a moment and interchange the integrals to get expected value of x as 0 to infinity probability x greater than equals to x. So whenever I am doing this, I am using Fubini's theorem. So first we have to check whether the conditions of the Fubini's theorem is satisfied or not. If it is satisfied, then it can be applied to these examples. We have a lot of we have an innumerable number of examples where this Fubini's theorem is applied. Now we think we have some idea about product space, product measure, and we have seen through this tutorial that how multiple integral problem can be handled using Fubini's theorem. Fubini's theorem is applied whenever we are trying to find or trying to establish some relationship like expected value of x as probability of x greater than equals to I and summing over I from 1 to n. So these sort of problems that we oftenly encounter in probability courses can easily be solved using Fubini's theorem. The interchange of the order of the integration, how they interchange, why they interchange, this can be established using Fubini's theorem. That's why this theorem is so important, and I hope this lecture gave some idea about the concepts of Fubini's theorem.